Yeah, good. All right, so the other thing that we're going to do is the second derivative. The first one, of course, was finding inflection values and intervals of concavity, is to come up with another test for local extrema. Remember, we already have one test for that, right? What was it called? The first derivative test. Remember, the first derivative test tested for relative extrema by using first derivative information, namely if the sign of f prime changed from positive to negative or negative to positive. There is another way to test for relative extrema, and it is called the second derivative test. So much like the first derivative test, it does determine if you have local max or mins, but this one uses second derivative information rather than first derivative information. So here's what the test says. Let's say you have a function and a critical value in hand. So remember, that's a value that makes the first derivative 0 or undefined. If you're in possession of those, you can actually determine if that is the location of a local max or min by plugging that value into the second derivative. And it turns out if your second derivative at the critical value is a positive number, then remember that means that the graph is concave up there. And if the graph is concave up like a cup, it's going to look like a smile. The only thing that horizontal tangent could be then, if the graph is concave up, is a local what? Min. Okay? Notice if the graph is concave up, the tangent line is below the curve. The tangent line is below the curve. And so that's going to be a local minimum value. On the contrary, though, if you plug in your critical value from the first derivative into your second derivative and you end it with a negative number, remember, Walter, means that the graph is concave down like a frown. Well, if the graph is concave down like a frown and you have a tangent line up at the top that's the slope of 0, that's going to be a local maximum. And notice if the graph is concave down, now your tangent line is not below the curve, but above the curve. So that's pretty cool. If your second derivative you already have in your possession, or it's a polynomial, something like that, and it's real easy to find, you can actually determine if there's a local max or min with a little less effort. You don't have to do two calculations. You don't have to check left and right. And the justification is a little bit easier too. You just look at the sign of the second derivative at the critical value. But there's two downsides to it. Number one, you do need the second derivative in order to use it. And as we saw yesterday, the second derivative is not always easy to get. And the other reason is sometimes it doesn't work. If you plug in your critical value into the second derivative and you get 0, that means that that value is also a possible inflection value, but that means that the second derivative test fails and you have to go back and try a different test, namely the first derivative test. Okay? So if you get a 0, it doesn't work. Let's try it out. Example 5. Find the relative extrema for this fifth degree polynomial. Okay, that seems pretty fun. The domain of this function is all real numbers. We need the critical values first. That's the first derivative. So we get negative 15x to the fourth plus 15x squared. That's never undefined because it's a polynomial. So if you factor out a negative 15x squared, you get an x squared minus 1, and you set it equal to 0 then. And you should get 3 critical values. You should get x equals 0, negative 1, and positive 1. Now you could set up the number line easily and test the intervals in between those 3 values, but we're going to use the second derivative test. So here's the second derivative. I'm going to come back up to that expanded version and take the derivative again. You get negative 60x cubed plus 30x, which if you want to factor something out there, you get a negative 30x times x squared minus 1. 2x squared, yeah, that's right. That was not going to work. That was going to give me a 0 for everything. That should be a 2x squared minus 1. All right, so now that we have kind of the factored version, let's plug in the critical values and see what we get. Let's try a negative 1 first. F of negative 1, when you plug it in, you're only interested in the sign, again, so not the actual value. You're going to get a positive in here and a positive there, right? So that's greater than 0. So here's your justification. F double prime, I forgot to put the double prime, F double prime of negative 1 is greater than 0. So greater than 0 means concave what? Up. If you want to come off to the side and draw your little positive man, You can see the bottom of his smile now. You don't have to do that, though. You just say, so f has a local min at x equals -1. If you do the same thing for 1, f double prime of 1, plug it in, you're going to get positive times a negative. Now that's a negative. If you get a negative value, you draw the negative guy. You can see him frowning. Now you see the local max on his frown. So f has a local max at x equals 1. And now if we try 0, f double prime of 0, when you plug it in, you get 0. So that's inconclusive. So the test failed. And we got 2 out of the 3. So what you're going to have to do now is determine what that is by the first derivative test. So I'm kind of deviating from the A and B. A and B had you do the first derivative test for all of them. I just went and did the part B. Now we do have to come back and test 0. So here's our little number line chart for the first derivative test. We got 0 right there. Now here we have to be careful. Since I have tested -1 and 1, I have to come back and pick a value that is to the left of 0, but not -1 or further. So -1/2, and then to the right, +1/2. If you plug those into the factored version of the first derivative, which is way up there, now you can get the sign of that. Well, the outside is always negative. So when you plug in a -1/2, you get a negative times a negative, which is positive. And if you plug in a +1/2, you get a negative times a negative, which is positive. So is there a local extrema at 0? No. And 99 times out of 99.5, if you get a 0 on the second derivative, that means that it's not only a horizontal tangent, but it's an inflection value as well. What? I'm plugging those in way up here. You got a -15x squared, so it's always negative outside. And whether you plug in a -1/2 or a +1/2, you get a negative number on the inside. And a negative times a negative is a positive. So they're both positive. But if you get that value showing up as both a horizontal tangent, like that, and a possible inflection value where the curvature changes, like this one does, concave down to concave up, then it's likely not going to be a critical value. But it still could be. So that's why you have to do the test. So now you would say f has neither a local max nor local min, not in France, but at x equals 0. So that graph did end up looking something like that, like the x cubed graph, or it could easily, it was increasing on both sides, yeah, so it had to look like that. That's an inflection value and a critical value. Yeah.
So when you are finding values to test, do you look for the midpoint between values, or do you?
Well, yeah, it kind of depends what you're plugging into. I usually choose the midpoint or something that's really, really close if it's not an integer. But like if you had a fraction like x thirds and you had to plug it in there, and you have to choose a fraction, or actually you had like 3x. Let's do that way. If you had something like 3x and you had to choose a fraction, you might want to choose like pi thirds or pi 6 or something like that, so that the 3's would divide out. It just makes it a little bit easier to work with. But really, truthfully, any value would work. You could have chosen -1/4 or -1/8. When you square it, though, -1/8 becomes +1/64. Okay, so that's the second derivative test. What's nice about it, here's what's really nice about it. This is where it earns its I guess its keep. It doesn't really earn a living, but the second derivative test does not require information or info left or right of the critical value. It uses the information at the critical value, which is really, really nice when you're given information that's not an equation or a graph, but rather a table of values. Because when you're given a table of values, you can't produce any more values. You're stuck with what's there. So maybe you'd like to choose a value to the left of a number in the table and a number to the right of the number in the table, but you can't if they're not in the table. All right? So that takes us to example 6. Wow, good segue. Selected values for a twice differentiable function. That means that the function is continuous and the derivative is continuous as well, because it's also differentiable. On the interval from -3 to 5 is given below, along with some selected values of f prime and f double prime. Okay, and we have f values there. Cool. Part A, is it safe to say that the graph is concave up from -3 to 5? Well, let's see. -3 is here. 5 is there. Concavity deals with which derivative? The second. Notice on the open interval between -3 and 5, the two values that I was given, or actually there's only one on the open interval, it's 4, and 4 is greater than 0. Can you assume then that the graph is concave up everywhere from -3 to 5? You don't have enough information. Just because it's concave up at 2 doesn't mean it can't be concave down anywhere else. No. We only have info. We only have info at x equals 2 on the open interval from -3 to 5. You would need a lot more information. All right, part B is a review. Explain why there has to be a z value between -3 and 5 where f of z equals 6. What kind of value is a z value? Is it an x value or a y value? It's an x value. So show that there's an x value somewhere between x equals -3 and 5 where the y value is 6. What theorem do we have for proving y values? IVT. Good. the IVT is the YVT. So here's how we did the IVT. You'd have to say the function is f. So f is continuous. You'd have to state that. And the function didn't, or the question didn't say it was continuous. It said it was twice differentiable. So you state that it's continuous, and then you could say f is continuous, and now you can find the y values at the endpoints. So you need f of 3, or f of -3, and f of 5. So you pull those from the table, the y values at the endpoints. You get 0 and 7. And now you could say, since 0 is less than the value we're interested in proving, 6, which is less than 7. The value that we want to prove, 6, falls between the y values of the endpoints. Since that, comma, by the IVT, and then you just reuse their words, there must be a, let's try this with notability. There must be a z from 3 to 5 such that f of z equals 6. If you paste that in as an image, you can shrink it down somehow. Y'all can actually copy text now. I'm not going to do that. That's ugly. Now it won't go away. I was just hitting, okay. You have to go to text to undo. Wow. Thank you. I did not know that. All right, so yeah, I'll just write it out there. There must be a z from -3 to 5, blah, 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 blah. Okay, you just reuse their words. So that's the IVT. Part C, explain why there must be a w between -3 and 5 such that f prime of w is 7.8. W is another x value, but now we're trying to prove that the derivative, which remember is the slope, yeah, that's going to be an MVT. The MVT is the slope VT, M for slope. So we need to give the conditions. And you don't have to say since, you can just say f is continuous on the closed interval from -3 to 5. By the way, up above when I said it was continuous, when you don't say where, that assumes that it's wet. Everywhere. I probably should have said f is continuous on the closed interval from -3 to 5, but you wouldn't lose points. F is continuous on the closed interval and differentiable on the open interval. You just state that, and now, according to the mean value theorem, remember f prime of x equals f of 5 minus f of negative 3 all over 5 minus negative 3. So f prime of x has to equal, let's see, f of 5 minus f of negative 3. We just figured those out. That's going to be 7 minus 0. So that's 7 all over 8. What does that mean then? By the IVT, right? So, now you'll say, so, by the MVT, yeah, by the MVT, comma, and then you reuse their words again, all the way to the end. There must be a W in the open interval from 3 to 5, negative 3 to 5, ... You can finish that up. So when they're asking you to prove a slope, that slope should be the value that you get when you do the average rate of change. Remember, this was the question I showed y'all when we came to the IVT the first time. It was the lowest scoring free response question ever on the AP Calculus exam. Out of 9 points, the average was 0.93 or 6 or something like that. All right, part D. This gets into what we're doing now. Does F have a local max, a local min, or neither at 2? Justify. Well, first of all, local extrema can only occur at what values? Critical values. So we need to see if x equals 2 is a critical value of f first. So that's in the chart. F prime of 2 is what? 0. So we got to say that. F prime of 2 equals 0. And now what do? We could either do the first derivative test, where we have your x and f prime, and you put 2 here, and you select numbers to the left like 1 and 3. Can we do that? We can't do that. First of all, we don't have the values in the table to choose those. And even if you did have table values that were left and right, you don't know if there's another critical value between the one you're testing and the one that you're using as a test value. So here the first derivative doesn't work. We need some other way to test for local extrema that doesn't require information on either side of the critical value. How about the second derivative test? So now let's see if we can figure out what f double prime of 2 is. F double prime of 2 is 4. Sweet. And 4 is greater than 0. So if you have a positive second derivative, draw the picture if you want. Now you can clearly see the bottom of his smile is a what? Local min. So this is your justification. The inequality greater than 0 is your justification. So f has a local min. Did it say to find the x value or the y value? Oh, it didn't say to find it. So f has a local min at x equals 2. That's it. That's your justification. Do we know what the local minimum value is? We do, right? It's f of 2. But it didn't ask for that. It just said, did it have one at 2? Yes, it has one at 2. Pretty nifty. Second derivative test. Yeah, but when you say 4 is greater than 0, the 4 has to be tied to f double prime of 2. Yeah, exactly what I have there in the box is what you'd write. Yeah. All right, that's it. Second derivative test. So hopefully you understand that one, and if that one showed up this year, y'all would score not 0.9, but 9. Yeah. All right, example 7. The graph of the derivative of f prime, a continuous function f. So we don't have the graph of f, but we know f is continuous. We have the graph of f prime, the derivative. The graph of f prime is better than a number line chart of f prime, because not only do you get to see the sign of f prime, but you get to see its relative values. Part A, on what open intervals is f decreasing? Justify. Remember, you can sometimes justify ahead of answering it. So if you want to, say f is decreasing when f prime is what? Less than 0. So now, since that's the graph of f prime, you want to know where those y values are negative. We got that, right? Yeah, from 0 to 1 and 6 to 8. So this occurs on the open intervals. You could say 0 to 1, union, 6 to 8. Are there any units to put there? No. So there you go. You've answered the question and you've justified it. You just did it in the reverse order, which is fine. At what values does F have a local min or a local max? Well, first of all, we can only have local extrema at critical values. So we need to see where F prime of X equals 0. Well, that's the graph, right? Or undefined. Is this graph ever undefined? No. So at least we considered that. It's equal to 0 at 1, 6, and 8. So underneath there, I'm going to put X equals 1, 6, and 8. And what you've done is you've now claimed them as critical values. So once you say that you've identified the candidates, now to be a local max or min, we need the sign to change. Does the sign of F prime change at 1? Yeah, it changes from negative to the left to positive on the right. So that should be a local what? Local min, right? Local min. Remember, we're not finding the local min of this graph. These are the derivative values. So if F prime changes from negative to positive, remember, F goes from decreasing to increasing. That's the local min. At 6, F prime changes from positive to negative, so that should be a local max. And at 8, F prime changes from negative to positive, so another local min. So we can clump the two mins together at 1 and 8. So here we go. F has local mins at X equals 1, comma, X equals 8, since F prime, same as it's always been, changes from negative to positive at X equals 8. So that's the first derivative test. Could you justify using the second derivative test? I think so. The second derivative test would be evaluating the second derivative at 1. Well, if we have the graph for the first derivative, what is the second derivative on this graph? It's the what's of the graph? The slopes. And what do you know about the slope at 1? It's greater than 1, or it's greater than 0. It's positive, right? And if it's positive, there must be a local what? Min. So you could use the second derivative test. You would just have to tie F double prime to the slopes of the graph. So it's almost easier just because you have the values to use the first derivative test. Since F prime, I'm sorry, I didn't finish this off here. Since F prime changes from negative to positive at X equals 8 and X equals 1 at both of them. And then, of course, you would say the other one, F has a local max at the other guy, X equals 6, since F prime changes from positive to negative at X equals 6. Or you could use the second derivative test. The slope of the graph is the second derivative, and at 6, the slope is negative. That means the graph is concave down, and the graph of F is concave down. You have a local max. Either way. On what open intervals is the graph of F concave up? F is concave up when the second derivative is positive. That's when the what's of this graph are positive. Slopes, right? So from 0 to 2, 3 to 5, and 7 to 8. Yeah, 0, 2, 3, 5, 0, 2, 3, 5, 6, 7 to 8. And then all you have to say is since the slopes of F prime are positive on these intervals. Again, you want to justify by relating it to specifically what's given. If you had the equation, you would show probably the derivative as F double prime. If you just say F double prime here, and you don't say somewhere that F double prime is the slope of the graph, you may not get full credit. Yeah. Is it 7 to 9? Yeah, it sure is. Thank you. Not only do I have tunnel vision here, but I have a bad short-term memory. Yeah, 7 to 9. All right, state the inflection values. So the inflection values of F are going to be where F double prime changes signs, yeah? Which is going to be where the slopes of this graph change signs. So that should be at the what's here? The local max and mins. The local max and mins of F prime are the inflection values of F, because that's where the slopes change from positive to negative, negative to positive. So let's just write that out right here. The local max and mins of F prime are the inflection values of F. I guess I should say not the local max and mins, the location of, that's better. The max and mins are the Y values. The location of the local max and mins are the inflection values for F. So those are going to be at, let's just list them up here where we can see them. X equals 2, 3, 5, and 7, right? Those are the 4 places where we have local extrema. Those are your 4 inflection values. And the justification could be what you wrote above there. That's fine. Now, part E. Sometimes they might ask you to try and determine where the graph of the function has an absolute max or an absolute min. This is kind of the same activity. It says, assuming that f of 0 is 0, sketch a possible graph of f, and then determine where it has its max and min. So they're giving you a starting value. F of 0 equals 0. So if we start at the origin, now we need to draw a prospective graph on top of this graph. So I'll use purple. So here's how you're going to do it. Remember I said earlier that if you know what the sign of the first and second derivative are on any interval, you know which part of the circle arc is going to have to graph. So anytime the slopes change or the signs of the graph change, we're going to reassess. So from 0 to 1, we have negative y values and positive slopes. Negative y values means decreasing, right? Positive slopes means concave up. The y values are the derivatives. The slopes are the second derivative. So with negative y values and positive slope, we're decreasing concave up. There's only one way to draw decreasing concave up. It's like that. So we'll draw it to, doesn't matter how far down you go. You're just going down, concave up until you hit x equals 1. Now from 1 to 2, we have positive y values, positive slope. That's increasing concave up, right? Increasing concave up. It may go back to the x-axis, maybe a little below, maybe a little above, who knows. From 2 to 3, we have positive y values, negative slopes. That should be increasing concave down, increasing concave down. Boom. From 3 to 5, positive, positive means increasing concave up, something like that. From 5 to 6, positive y values, negative slope. So increasing concave down to 6. From 6 to 7, negative y values, negative slope. That's decreasing concave down. From 7 to 8, negative y values, positive slope. That's decreasing concave up to about 8. And then finally from 8 to 9, positive, positive is increasing concave up. Somewhere to there. Now there's a possible graph of f, so I'll label it as f. Notice the local extrema, they line up perfectly now, where we said they were. And the inflection values also line up perfectly. Is it possible from this to determine the absolute maximum value? No. We kind of just went up and down kind of arbitrarily, but it looks like that local max and that endpoint, one of them could just as easily be above the other as the other way around, right? So without any kind of quantifiable analysis, which we really can't do from this graph, we're not sure which one of those is the highest. We know one of those is going to be the absolute max. So for the max, for the max, it's inconclusive. The absolute max, we can't tell. But what about the absolute min? Is there any doubt where the absolute min is going to occur? No, it should be at what? It should be at 1. Okay? The absolute minimum is at 1. So we have a min at x equals 1. And there you go. So that little activity that we did of sketching a graph from the derivative function, pretty nice. Get your y values, get your slopes. That'll tell you if it's increasing, decreasing, concave up or down. All right, cool. That makes a good pre-response question for like next Tuesday, which is kind of why I wanted to cover this section. So you'll have one that looks similar to this. All right, example 8. It's the last one. We'll get through it. We're in here until 11:40. Oh, yeah, I'm looking at the regular schedule. We're on Pepper, 11:20. Okay. All right, the graph of the derivative f prime of a continuous function is shown below. So again, f is continuous. This is not the graph of f, though. This is the graph of f prime. F prime, obviously, is not continuous, but it tells us the function f is. Same thing. On what intervals is f increasing? F is increasing when this graph is what? Positive. So that would be from 0 to 2, union 4 to 6, union 8 to 9. And then the reason would be since f prime is greater than 0 on these intervals. Part B, where do you have a local max, local min? All right, let's get the critical values. The critical values are where the derivative is 0 or undefined. Critical values equal to 0 at 2, 4, and 8. So let's say that. F prime equals 0 at x equals 2, 4, and 8. We usually consider it first, but this time I didn't. So as long as you're considering it, that's fine. Does f prime ever equal d and e? Where? 6. Guess which critical value most students would forget to consider? 6. Right. It tells us that it's in the domain of the function because it says the function f is continuous, but the derivative is undefined at 6, so that makes it a critical value. That would be like a vertical tangent or something. All right, so now I got to see if those are local max or min. At 2, f prime changes from positive to negative, so that's going to be a local max. I'm not going to write it all out, but the justification would be f has a local max at x equals 2, since f prime changes from positive to negative at x equals 2, right? That would be the first derivative argument. That's probably easier than the second derivative, talking about the slope. At 4, the graph changes from negative to positive, so that should be the location of a local min. F has a local min at x equals 4, since f prime changes from negative to positive at x equals 4. Let's do the other one over here at 8. That's negative to positive. That's another local min. So you can kind of throw that into the same justification as you did with x equals 4, kind of like we did earlier. Put them together. Now at 6, let's see. What's the value of the derivative just to the left of 6? Positive. And just to the right of 6? Negative. Is that going to be a local max? Yes. So you've already claimed it's a critical value, so you don't have to say that again. Now you just say f has a local max at x equals 6, since f prime changes from positive to negative at x equals 6. The exact same sentence. Okay? It didn't happen through a continuum, but that's okay. So all of them ended up being local extrema. Where was f concave down? F is concave down when the what's of this graph are negative? Slopes. So again, from 0 to 3, exclamation point, right? That's it. 0 to 3. So you would say 0 to 3, and then, of course, the reason would be since, don't just say since f double prime is negative, bless you. Say since the slopes of f prime are less than 0 on this interval. Relate it specifically to what you have. State the inflection values. The inflection values are going to be where the slopes of this graph change, right? So definitely at 3. The The slope's changed from negative to positive. What about at 6? The slope to the left is positive. The slope to the right is positive. So we only have one inflection value, and it's at 3. Okay, at x equals 3, since the slopes of f prime changed from, I think they went from negative to positive. Yep, from negative to positive. So don't really ever get in the habit of saying since something goes from increasing to decreasing or decreasing to increasing. Always talk about a sign change in something, positive to negative or negative to positive. And then the fun part, I'm going to let you try it on your own here. I'll graph it with you quietly, but you do it on your own. Again, assuming f of 0 equals 0, sketch a possible graph, and then determine if you can see what the absolute max and min are on the closed interval. So make sure that you're looking at the y values and the slopes. Is the graph increasing or decreasing? Is it concave up or concave down? And do it on the same graph. Oh, x equals 0. Yeah, I was just doing it without looking or paying attention. That's better, right? So real quickly, if you haven't got it yet, you're starting at the origin. It told you that. From 0 to 2, it is positive y values, negative slope. So it should be increasing concave down. It has to look like that. From 2 to 3, it's negative, negative, so decreasing concave down. Then from 3 to 4, it's negative, positive, so decreasing concave up. Now 4 looks like it could be the local min or an absolute min. But we know we don't come down as far as we did when we started. Because notice, what's that?
There is an email for teachers to check.
Uh-huh. That's what the question was asking.
It's going to be on the YouTube, and the channel is called NBHS TV.
Got it.
So teachers, if you want to see the
we can't tell what the absolute max is because, again, the right end point, that's a cusp right there. The cusp may be taller or the right end point may be taller. We're not sure. But we do know there's an absolute min or a min at x equals 0 now that we fixed that. Here's why you know this. It's going up from 0 to 2. That's like a 2-second span if you want to think about it in terms of time. It's going down for 2 seconds. So how do I know that it doesn't get back as low as where it started? Yeah, look at the y values. The y values are the slope. It is going up at a rate that starts out at 3. and it stays 3 for quite a while. We're only going down ever at a maximum rate of 1. And so we're going up a little bit faster than we're coming down. Even though the time or the x values still span 2 on either side, it doesn't get as low as where it started. So you could still do that. That's not a quantitative analysis. It's still considered qualitative, but you are thinking about some type of number. 3 is bigger than 1. So the speed essentially is bigger going up than coming down. So for sure there's a min at x equals 0. All right, and there you go. So if you could do that graph and answer that type of question, you're in good shape. And notice we drew a continuous function. If it didn't say f was continuous there, we could actually draw something like an open circle up there. Right, exactly. Yeah, if it wasn't continuous, you could put an open circle there at the top of the cusp and put a y value way down here. Yeah, so that would have to be continuous to say it's a min. If your slopes actually went to, if there was a vertical asymptote right here on the graph of f prime and f wasn't continuous, then f could also have a vertical asymptote because the y values and the slopes would go up to infinity. Infinite slope is approaching vertical, and of course infinite y values goes up forever. So there it is. We got it. With a little help from y'all, I even found the min at x equals 0 instead of the local min at 1, which I don't know why that was there. We'll blame Scooby-Doo.